Hello. We're going to talk about resistors more and resistive circuits, and then more about energy and power in this lecture. So by the end of it, you'll be able to do more calculations and have hopefully a better appreciation of the distinction between energy and power and how to calculate it and measure it in some of the circuits that we're going to be working with over the next week or two. As a warm-up, to get you back to what we had been doing last time, see if you can figure out the current that would flow through a resistor that is a value of 20 ohms that's attached to a battery that has a voltage of 12 volts. So please calculate the current in the circuit, and also, if you can, select which choice is the best one for how you would measure current in the circuit and how you'd measure voltage in the circuit. Remember, use an ammeter for current and a voltmeter for voltage. You'll be doing that in lab soon, but I want you to see a picture of how you do it so that when you do it in lab, you'll have a better understanding of how to set it up. And there's the answers. So we talked last time about parallel resistors when they're placed such that you have, here's your battery right here, remember that's the symbol for the battery, and you have current that can flow through this, down this resistor, and you also have current that can flow down this resistor. And at this junction right here, the current has to choose whether it's going to go that way or that way. And the truth is some of the current will go through resistor R1 and some of it will go through resistor R2. The exact amount depends upon the relative value of those resistors. We will be talking about that. One of the things that I'm going to want you to see, and I'm going to show you why this is the case, is that when you put a few resistors in different configurations, it's the equivalent of having one resistor. So in other words, these two here that are in parallel can be equated to just one resistor right here. And I will derive why this is the case soon, but the equation for finding that out is this one here. If you take the value of R1, and R1 is going to be in ohms, and you take 1 over it, and you add it to the value of R2, 1 over R2, again, R2 is also in ohms, add those two together, and then take the inverse of it, that's going to be the value of your equivalent resistor. Let me give you an example. Let's say that R1 has a value of 2 ohms, and let's say that R2 has a value that's also of 2 ohms. So if you take 1 divided by 2 ohms, you get a half. You add it to another 1 divided by 2 ohms. So in other words, if you have two resistors in parallel, to find the resistance that the battery would see here, if both resistors have 2 ohms, you're adding 1/2 plus 1/2. That gives you 1, and the units are 1 over an ohm. If you take the inverse of that 1 over an ohm resistor, you're going to get that it's 1 ohm, which may seem funny. You have two ohm resistors, you're putting them in parallel. Your result is a resistor that actually has a smaller value. That's always going to happen when you put resistors in parallel. We'll talk about why more, but this is an equation that will allow you to find what we call the equivalent resistance for two resistors that are put in parallel with one another. With series resistors, the equation is actually a little bit simpler. With a series resistors, you'll have one resistor here and another resistor there. Notice that there's only one path for the current to follow. It can't choose to go a different junction here because there isn't any other junction. It has to go through R1, then it has to go through R2. So in other words, it has to go through two different hurdles. You can think about it like that. It has no choice. Current here is no choice. It has to go through both resistors, and each one takes a little bit of effort for the current to go through. So when that's the case, you could imagine that two resistors in series are going to result in a greater obstacle for the current to have to travel through. So in this case, the resistances add. And so the battery here, if you want to write what this circuit looks like, by combining these two resistors into just one resistor, you would find that these two resistors would add together to get the value of this single resistor right here. So for series resistors, to find the equivalent resistance, you add the two resistors together to get the result. So in other words, if this was 2 ohm resistor and that was a 2 ohm resistor, same value in this case, they don't have to be, of course, but they could be. Add those two, you get 2 plus 2, you get 4 ohms. This battery is going to experience having a 4 ohm resistor. Battery doesn't know whether it's 2 2 ohm resistors in series or just one 4 ohm resistor right there. That is what we do for series resistances. And I'll also explain this later, but I thought it useful for you to see the formula right now for parallel and series resistances. This will appear on the next homework. And we talked about this last time. Current through all series resistors is going to be the same, but the voltage can be different. It is different if the resistances are different values. If they're both the same value, like they're both 2 ohms, then the voltage drop across both resistors will be the same. But if they're different resistors, then each one will have a different voltage drop across it. This is a really important concept, and we will calculate it later. But conceptually, I wanted you to see it now. Now I'm going to ask you to continue the thought process. Imagine you have 2 light bulbs that are in parallel. Now light bulbs, in this case they're actually light emitting diodes, they're going to look something like resistors. They're going to have basically an equivalent resistance as far as the battery is concerned, because it takes effort for the battery to pump electrons through lights, just like it does to have them pump electrons through resistors, as you'll see in lab. Let's say each of these light bulbs has a resistance of 20 ohms. Let's think about how much current is pulled out of the battery, or passes, you could think it passes through the battery. It also passes through each of the light bulbs when you have both of them that are in parallel like this. What if one of them, let's just start with just one of them being turned on, which means we basically get rid of one of them. So if I got rid of this one on the right, and you only have this one right here, and you have a 12 volt battery and a 20 ohm light bulb, how much current is going to be passed through, is going to pass through that? Next, let's turn on another one, so that instead of just having one here, you actually have 2. And then finally, let's do it with 3. What are you going to have in that case? What current, total current, is going to pass out of the battery's terminals through the light bulb in each of those cases? So we're going to be talking here about basic principles of energy that you've seen a little bit before in first semester physics, but we're going to see it again as it relates to electricity. And like I said in a previous video, the units of energy are the same, whether it's electrical energy or mechanical energy, which I think is just great. It's the same unit of energy. It's the same thing we're talking about, just different forms of it. You can convert from one to another, and that's a little bit about what we'll be talking about. And when you convert, some of the energy becomes heat, and that's considered to be energy that's lost. Although, as I said in first semester class, it's not really lost, but it changes form. So it's lost in one regard, but it doesn't go away. When it becomes heat, you can't recover heat very easily to create mechanical energy. You're not able to get it all back. So in that sense, it's lost, but the energy still exists. It just exists as heat. But the amount of mechanical energy that you get when you convert from one form to another, that percentage of it that you can actually convert is called the efficiency. And you've probably heard about things being 100% efficient or 90% efficient or 30% efficient. That refers to the amount of energy that is converted from one form to another. If it's 100%, then you got all of it. If it's 30%, then you only got 30% of the initial energy transformed into a new form that you're hoping to use. And as you remember from first semester class, there's several forms of energy. You got kinetic energy, that's the energy of motion. You got potential energy, that's in terms of gravitational potential energy, that's the energy associated with height, or objects that are higher up have a greater potential to be moving really fast when they hit the ground. So higher up means greater potential energy. If you're on top of a building or top of a cliff, you have greater potential energy, because if you drop something, it can be moving really fast when it hits the ground. Then you can also have elastic or spring potential energy. It's still potential energy, just a different form. It's not gravitational. But when you pull back a spring or you pull back the bow of an arrow, you're giving that arrow the potential to be moving really fast. So that's potential energy also. Other forms of energy include thermal energy, which is when it's transferred, we call that heat. That is, as I said, it's if you convert from, say, kinetic energy to heat, and friction causes that to happen, you can't easily get that heat back to create more kinetic energy of some large object. So it's kind of like a loss. We think of it as a loss, although it's, like I said, it's not really lost. And then, of course, you can have other forms of energy like chemical energy, which is another form of potential energy because the molecules are arranging themselves such that you can extract energy from them. Or for that matter, nuclear energy, which again is another form of potential energy where you have energy wrapped up in materials that you're releasing, and it's released as heat, which again may seem like a loss because you can't use that easily for moving things. And we're going to talk about solar energy as well. And we'll spend a lot of time talking about light, particularly towards the end of the semester. But solar energy is an important part of renewable energy, which is really important for us as we try to transition into other forms of energy besides burning things, burning fossil fuels mostly. So solar is a really important form of energy that we will discuss a bit. And I think I will stop this video here, and you'll pick it up, continuing to talk about energy and power.